The next thing I want to talk today is question decomposition, this beautiful topic. So there are many articles. For example, this article, Explainable Multi-Hop from Saeed Shikarpur, Dayton University, is inspired by really this article from Hanan Haji Shirazi from Washington University. And she's a really good researcher. And there is also another alternative way, which I will explain in the next lecture, which is unsupervised question decomposition. Because in this approach, we want to see, of course, this is just a pseudo-decomposition. We find this pseudo-decomposition and when we give it to the transformer model and then so on. So I will explain it in the next lecture. But let's focus on this lecture, this article and this article. They are very related. They use it. For example, this one uses this article. So we review the pool net. As I said, after decomposition, you can do it in several ways. Assume you have a decomposition. So this is the topic entities of sub-question 1, topic entities of sub-question 2, and this is the topic entities of sub-question n. And each sub-question has, for example, k number of subtopics, let's say. So you extract each of them, you see what are the relationship. Oh, by the way, this algorithm could be used for both text and knowledge base. For example, D could be knowledge base, T could be text. And so we extracted until you find the solution. You expand the graph until you fall. So this is the algorithm in PoolNet article. And then we have graph MDR, which is suggested by this article. Let's focus on question decomposition because it's very important nowadays. So the input query is considered as, so this is W1, Wn. So we map it to C points. I will explain what do I mean. And then we see which of the indices maximizes this probability. So the article, so of course this approach, as I said, is inspired and is inspired by this article from Washington University. So as you know, these authors, they noticed that 47% of this hotpot QA, this data set are related to bridging questions, and 23% are intersection questions, and 22% are comparison questions. And it's interesting that the remaining is just 8% that we don't know which category there are. So we should define other categories just for this 8%. But it's so strange because 8% is so small. So in hotpot QA, we find 92% of multi-hop questions belonging to either bridging, intersection, and comparison. For example, this is an example of bridging. So we have 400 labeled examples that they're enough. The authors claim that these are enough to see which category they are in. And the global risk scoring approach, we consider each decomposition, I mean the sub-questions and their answers, to select the final answer. For example, when it says which team does the player name this one play for, it decomposes this question into two questions. The first one, which player named this one? And the second one, which team does the answer play for? So question 2, so if there is a causal graph, question 2 is dependent on question 1, because question 1 you get the answer and you use this answer to encode the question 2, and finally you solve the answer for question 2, which is the answer for the original Q question here. So we just need to find the span that we should pay attention to, because we can decompose it by these spans. In this article, they call it points. So these points, for example, we have a sentence, blah, 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 and we have some points that separates them and creates some sentences. For example, S1, S2, S. So we create some sentences by some points that it's like a separator. It separates sentences from each other. And the decomposer, see, is their algorithm. So it's either bridging, intersection, comparison, and so they decompose the original question. For example, Ralph was a psychology professor at which university? So if it is bridging, so we say it has two questions. So this question is, let's say, it is composed of two questions. Or if it is intersection, if it is composed of two other questions. Or if it is comparison, intersection of answer 1 and answer 2. So it produces 3 questions instead of 2 questions. So it's a little bit complicated. So we decompose in 3 steps. And as I said, we should just see that it belongs to one of these categories. And each sub-question can be formed by copying and lightly editing a key span. And these things are you are doing manually. There is something rule-based that some people don't like, but it is nice. At least it works. So what is the training for span prediction for sub-question generation? So, for example, for bridging, we only need 3 points. For intersection, we only need 2 points, this point and this point, for example. For comparison, we need 4 points. Start of the first word, end of first word. Start of the second word, end of the second. We are comparing them. So, for example, when I say pointer 4, it remains that it refers to the comparison, because we need 4 points to separate them. And the span prediction for sub-question generation, so we train a model that learns to map a question into C points. So we are pointing a question to some points, C1, C2, C3. We just need to know these points in order to separate them and also make sub-questions. So this is the algorithm. The only thing you should know, we are training using W. We are training it. And so U is just the BERT of S, because we just use that pre-trained model, BERT, as we do in several algorithms, several articles. And now that we have encoded this question, because look, this U is BERT of S, and S is a sequence of words in the input sequence, in the question. And so we have encoded the BERT into U, so this is the question. So what is the relationship between the question and the Y? And Y is, for example, P is the probability that the ICE word, the ICE word is the J's index produced by the pointer. The model extracts C indices that yield the highest joint probability at inference, of course. And for span prediction, this is a good example. For example, which team does a player named blah, 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 blah play for? So which Q, this is the team, the Q in index 1 is the team, because by doing team and play, we can separate it, we can see what is the span of that. So depending on the category, for example, here the category is bridging, we have a set of rules. So this is for bridging, intersection, and comparison. So team is the start of the span. Now that we have done this for this bridging example, let's do it for intersection and comparison as well. So for intersection, we say that, for example, index 1 is results. So this is the index 1, which results stories USA started, because we need index 1. So we have three sentences, S1, S2, and F3. S1 spans from index 1, everything until index 1. Sentence 2 starts from index 1 and reaches index 2. Sentence 3 starts from index 2 until the end of the sentence. So we have two questions from S1 to S2 and from S2 to S3. So we have two questions. So this Q is decomposed into Q1 and Q2. The same thing for comparison. It's very easy to understand these things because it's just some rules that we, of course, for find OP is an algorithm that is written here. And so the goal of single hop reading comprehension is so easy. The goal is to obtain the answer and evidence giving sub-question and subgraphs. So the answer is a span from one of the paragraphs. If this belongs to the paragraph, we say yes, otherwise we say no. And now here we are using reading comprehension. As I said, we encode it using BERT, and finally we know the start and end. What is the start? What is the probability of start? What is the end? So we use softmax for all of these things. And finally we have decomposition score. And that's it. So we can connect different fields, ideas, paradigms. It's good. It's like making the Markov chains of your brain, that you go from one idea to the other idea more ergodic, so that in the infinite limit it reaches your probability distribution. I mean your final stationary distribution, which is the final goal of humanity.